Have you ever wondered if music could just write itself? It sounds a little like science fiction, right? Well, today we're going to explore how some really elegant mathematical formulas can generate these complex, evolving melodies that sound, well, surprisingly alive. So let's just dive right in. This right here is the core idea, the whole philosophy behind the Pdida library for pure data. It's a pretty radical shift in thinking. See, we're not composing notes one by one. No, we're designing systems to find them. It's like the music is already in there, hidden somewhere in the logic, and our job is to just pull it out.
Okay, I know what you're thinking. This looks intense, right? But trust me, this is our playground. Every single one of those little boxes holds a simple mathematical expression, just a single line of code. And when you put them all together, they create this whole ecosystem where numbers get bent and folded and filtered until, poof, they become music.
So here's what we're going to do. We're going to break down 5 of the fundamental techniques from this library. Think of it as opening up the Generative Composer's toolkit. We're going to see exactly how these incredible melodies are built, right from the ground up.
All right, first up, Bitwise Geometries. This is probably the most purely digital sounding of all the techniques we're going to look at. We're getting right down to the absolute fundamental building blocks of numbers here. You know, when we see a number, say 12, we just see 12. But a bitwise operation, it sees its fundamental DNA, the ones and zeros that actually make it up. And by messing with that binary code directly, using things like an XOR operator to flip bits around, we can create these really radical, totally unpredictable changes in a number's value. And those changes, that's our melody.
So what does that look like in practice? Well, imagine taking a stream of numbers, that's our melody, and then you just collide it with a slightly shifted version of itself. This crash happens right down at the level of individual bits, creating this kind of digital interference pattern. It's like a controlled chaos that we then channel into a musical scale.
And the result? Honestly, it sounds like a circuit board just decided to wake up and start singing. You get these sudden, sharp jumps in octaves, these incredibly detailed, almost fractal-like arpeggios. And what's really cool is, because different bits are changing at different speeds, the sequence feels like it has a memory. You get these variations that don't show up right away, but only over these really long cycles. Okay, so we've just been in this jagged, super digital world of bitwise stuff. Now let's totally shift gears and look at something way more organic. We're going to use classic wave functions, but not to create sound. We're using them to shape the melody itself. Yeah, we all know sine waves from, making synthesizer sounds. But here, they're not making the sound at all. They're creating the shape of the melody. And the result is these just incredibly graceful, natural-sounding melodic curves. And here's how that works. You take 2 different wave functions, picture 2 ripples overlapping in a pond, right? And you multiply them together. That creates a much more complex kind of beating pattern. Then you take that super fluid curve and just map it to musical notes. It's like you're laying a musical scale right on top of this natural wave. And the effect is, it's almost physical. You get these pendular melodies, swinging back and forth, rising and falling with this really natural grace. They actually slow down at the peak of the curve and speed up in the middle, just like a pendulum would. Or even like the rhythm of breathing. It is absolutely perfect for creating those floaty, ambient textures. All right, now we get to the really smart part of the library. And I say smart in quotes, but this is where we actually introduce decision-making. We're going to let the melody react to itself and, change its own course. At its heart, this is just simple if-then logic. So imagine our melody is climbing up a hill. The algorithm is constantly checking something like, hey, is this note higher than the last one? If the answer is yes, maybe it decides to jump all the way back down. If no, it just keeps on climbing. That one simple decision point can lead to these really dramatic shifts in where the melody goes. And this leads to some really fascinating musical behavior. You'll get melodies that are climbing, 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 and then suddenly they trip over a condition and just jump backwards. Or sometimes they get stuck on a single note, creating this little plateau of tension before it finally resolves. It sounds so intentional, almost like how a person would actually phrase a melody. Okay, on to our 4th technique. This one is all about one of the most powerful, most common tools in all of generative art, the modulo operator. And here, we're going to use it to basically fold and distort melodic space. Now, the modulo operator sounds way more complicated than it is. Just think of a clock. If I say it's 14 o'clock, you know that's 2 p.m.
Well, 14 modulo 12 is 2. It just gives you the remainder. That's it. And by using this over and over, we can take a sequence of numbers that wants to just keep getting bigger and bigger, and instead we force it to wrap around on itself. And that's how you get these beautifully complex looping patterns.
So why 13? Well, it's a prime number. And here's the trick. When you use a prime number for your modulo, the patterns you get don't resolve so easily. They create these wonderfully long, really intricate cycles that sound way less predictable than if you just used a common number, like 12.
The result is what's called a scanning algorithm. The best way to picture it is like a laser beam bouncing around inside a grid. The melody just jumps all over the place between different registers in this really granular way. And this creates these complex internal rhythms. It sounds a bit like an old-school analog sequencer that's just been pushed way, way past its limits. All right, and finally, this is where it gets really exciting. We're going to start combining all these different techniques to create something totally new. This is where the whole becomes way, way greater than the sum of its parts. So check this out. We're basically mashing our techniques together. Imagine you've got two different rhythmic cycles, both running at different speeds. We merge those together with a bitwise operation, which makes a new, more complex pattern. And then we just layer a third cycle right on top of that. What you get is a final melody that is just constantly shifting and evolving.
And that right there, that is the essence of emergence. You can understand each of the individual pieces, but there's no way you can predict what the final output's going to sound like. It creates these really dense, evolving melodic lines that just feel like they have a life of their own. This is the perfect engine if you want to generate infinite, non-repeating music.
So we've just looked at this incredible toolkit of mathematical tricks. But what does all of this actually mean for the person making the music? Well, it pretty much completely reframes what it means to be a composer. And that's really the big question, isn't it? As the programmer, are you the composer? Or are you more of a curator of processes? Think about it. You're not choosing the notes. Nope. You're choosing the slope of a curve, or the friction of a bit mask, or the logic of a decision. You're not writing the music. You're more like a gardener, cultivating the conditions where the music can grow all on its own. And I think that's the real beauty of all this. The algorithm isn't some cold, heartless machine. It's a chaotic system. But it's a chaos that's been harnessed by a really elegant formula. It's kind of proof that sometimes the most amazing music isn't something you write, but something you find by building the little universe that allows it to exist in the first place.